Okay, so the fourth talk is on incorporating visual semantics into sentence representations within a grounded space, and will be presented by the first author, Patrick Borges.
So, good afternoon. I'm going to present a work that we did at Leipzig, Paris, when we applied the principles of language grounding to sentence representations. So first, I'm going to talk about what language grounding is. So as you know already, the basis of distributional semantics is the distributional hypothesis that was formulated by Harris in 1954. And it states that words that appear in similar contexts in text tend to have similar meanings. So, as you know, when we browse huge corpus of text, the meaning of the word moon, as it co-occur with other words, should be close to the meaning of words such as sun, stars, stuff like that. And this hypothesis is the basis for distributional semantic models, such as the well-known word2vec. In these models, we learn the vectors that embed words, and these vectors are chosen to maximize the probability of these words to co-occur with other words in text. Now, these distributional semantic models are intrinsically limited, and that's the intuition of language grounding, because they're only based on textual information, and they lack a lot of perceptual information about, say, the appearance of objects, their color, their shape, etc. On the other hand, we, as humans, always have a grounded understanding of language, because as we learn the meaning of words and concepts, it's always in a perceptual setting, with perceptual knowledge intrinsically linked with our experience. So there's a consensus in cognitive psychology now that our human understanding of words and concepts is linked to our motor systems and perceptual systems. So I'm just going to give two examples to illustrate that. First example, when perceiving action verbs such as kick or punch, the regions of the brain corresponding to the leg and arm are activated. Second example, one showed an image of a pumpkin and asked to name the object. If the image is orange, the answer will be very fast. If the image is grayscale, it will be slower. If the image is in another color, it will be again more slow. So that was the first element to justify grounding. Our understanding of words as humans is intrinsically linked to perception. Now, the second element is called the human reporting bias, and it is very simple to understand. Basically, it says that what is written in text is entirely different from what happens in real life and in images. So that's what Gordon and Al noticed in their paper. They noticed that the frequency at which objects, relations, or events occur in natural language are significantly different from their real-world frequency. So what they did to demonstrate that was they browsed a huge corpus of text, and they looked for occurrences of action verbs. So these are the action verbs and the number of occurrences, and they were quite surprised to notice that, for examples, humans are murdered 5 times more than they inhale, or that humans are thousands of times more late than on time. And this can be explained quite simply, because in text we never write about what is obvious. We never write about that bananas are yellow, that pumpkins are orange, stuff like that. We only write about unusual stuff. And so that was the second element. We need images and we need perceptual information to ground the meaning of textual representations. So these considerations have led the researchers to formulate a new distributional hypothesis, more general, in which words that appear in similar contexts, whether in text or images, tend to have similar meanings. So for example, for the same word moon, by looking at images, we can infer more information, more perceptual about its shape, color, etc. So now, the first applications were for word embeddings. We have two families of models. First, on the left, the sequential models, in which textual and visual representations are built separately and then joined, then combined afterwards. So this is an example by a work of Collet and al., in which they learn a projection from the word-to-vec embedding to the visual representation of the object for a bunch of 5,000 concrete objects. And the multimodal word embedding is the concatenation of the word-to-vec embedding and the projection of the word-to-vec embedding. On the other hand, we have the joint models, in which both modalities, textual and visual modalities, are leveraged jointly during training. And it's closer to the way that we humans acquire perceptual knowledge about words by jointly leveraging textual and visual information. Here, I give the example of a word by Lazaridou and al., in which the training objective is a linear combination of a word-to-vec objectives, so that's the textual information, and a visual objective, which is a cross-model ranking objective for visual information. Of course, the next step was to do sentence representations. That's the ground set models. So here in this model, it's a sequential model where a skip thought vector is concatenated with a grounded vector, and the grounded vector is learned by optimizing two objectives, an entailment task and a cross-model ranking task. Now, the limitation of this work is that first, at the same embedding size, the performance of the multimodal model is inferior to the textual baseline, which is a big limitation. It's a sequential model, so maybe a joint model will be better, and it relies on learning cross-model projections between sentences and images, and we're going to propose another approach. So very briefly, I'm going to give the intuition behind our model. So first, we began by listing the differences between sentences and words. Very simple differences. A sentence for a given image, we have a quasi-infinity of sentences describing that image, which is not true for words. Second, a sentence can carry non-visual information that is not in the image per se, but comes from our human understanding of the scene. For example, here we can infer that the little bears are the cubs of the mama bear. Finally, for a given sentence, a quasi-infinity of images can apply, so sentences can be visually ambiguous. From these very simple considerations, we can derive hypotheses. Since we have a quasi-infinity of sentences describing a given image, we impose that sentences should be close in the embedding space. We call this information the cluster information. Since sentences carry non-visual information, we don't want to project images containing closed images to the same points of the visual space, so we rather impose a constraint that similarity between two sentences should be close to the similarity between their corresponding images, respective spaces. Finally, as we want to preserve the non-visual information in sentences, we don't apply the perceptual and cluster constraints in the textual space, but rather in an intermediate space. This way, textual semantics can benefit from the visual losses without degrading the semantics brought by the textual objective. How to modelize this? This intermediate space is learned by learning a projection G between the textual and the grounded space. The cluster loss is a very simple max margin triplet loss, bringing sentences corresponding to the same image together. And the perceptual loss is we maximize the correlation between the similarity of two sentences and the similarity between their corresponding images. So to finish for the modelization, what we learn is a GRU sentence encoder by jointly learning, optimizing a textual objective, which is a skip thought objective, and a visual objective, which is a combination of the aforementioned losses, the perceptual and cluster losses. The textual loss is it's learned on a textual corpus for the textual information, and the visual losses are optimized on a visual corpus for visual information. Talking about the data, for the textual corpus, we used the Toronto Bookset dataset, which contains a huge number of sentences, 74 million sentences, ordered sentences, coming from a set of thousands of unfinished novels. So it's a very rich textual information. For the visual corpus, we use the MS COCO dataset, which is a very well-known image dataset with roughly 100,000 images, and each image has 5 descriptive captions. For the baselines, so our textual model, a textual baseline is the skip thought model. So in the skip thought model, the objective is to learn the previous and next sentence in a textual corpus. The ground set models of Kela, of course. Our sequential baseline was a work that I already talked about in the introduction, sequential. And a projection baseline is the joint model that we present in the introduction. And for the 2 last models, what we did, we just use sentences instead of words. So these were models devised for words, but we used it for sentences. For the results, so first we analyzed the impact of visual grounding on textual representation. So we compared our multimodal model with the textual baseline. First experiment, semantic relatedness. Well, the goal is to align the cosine similarity of 2 sentences with human judgments. So we have a data set of pairs of sentences with human annotators saying if the sentences are entailed or not. So here we have T, the textual baseline, and last row is our multimodal model. We see that there's a huge similarity gap. We manage a lot to align with human judgments. And we use the STS dataset, and in the STS dataset, it's divided into 3 sets of sentences. We have captions, news, and forum. And what we did is we computed the concreteness of those dataset. So captions is a very concrete dataset, and that's why we have a huge gap, around a 43 gap in performance. News and forum are less concrete, and we have a lesser gap. So the first observation is that grounding can bring useful information, especially when sentences are concrete. This observation is strengthened by a qualitative experiment. So we use a CM Places dataset in which we have a set of visual scenes, say basilica, boxing ring, stuff like that. And each dot is a sentence. On the left, we have the Disney with the textual model, and on the right, with our multimodal model. And we observe that our model is much more able to separate visual scenes. Now, another question: what happens for sentences which are less concrete? So we build artificially abstract sentences using abstract words, such as love, horrified, tragedy, and we looked at the nearest neighbor given with the textual model and our multimodal model. So we observe, just for the first example, two people are in love. With the textual model, it gives 2 people are fencing indoors, so no relation. And with our model, a couple just got married or are taking a picture with family. So with our model, it was done on the Flick 30K sentences. We are much more able to capture the meaning of abstract words. Just a few words on quantitative results. So we use the Centival framework. So the first rows are the ground set models, then textual baseline, our projection sequential baseline, at the end our models, and all the different tasks are taken from the Centaval framework, and at the end we average the results. So very short informations. First we observe that multimodal models are better than the textual baseline, which is a good fact. We observe that the ground set models are inferior than the textual baseline, but are better than the textual baseline when the embedding size is divided by 2, which is coherent with their paper. Then we observe that our approach based on the cluster and perceptual losses are better than the projection baseline. And finally, that the joint models are better than the sequential models. So I'm running out of time and the presentation is finished. So do you have any questions?
Thanks for the talk. I was wondering if you tried this approach with like state-of-the-art, like deep language model like BERT, and maybe changed the loss to accommodate your ideas, and whether this would...
No, we didn't, and we should have, and it's, of course, a future work we should do,
Okay.
of course.
Cool.
You're right.
Maybe a quick last question. So this might also be maybe future work, but are you looking at more downstream tasks? So the extrinsic evaluation you mentioned, but also what about, would it help, would this grounded space help improve performance on VQA or other sorts of downstream vision and language tasks?
Of course, I think there's a lot of applications like that to do. Our goal is to look at really textual tasks to see if visual information is able to help just on what should be purely textual tasks. And of course, well, we should be looking visual question answering, visual question generation, stuff like that. That's what I'm doing with a colleague.
Great. Let's thank the speaker.